We would now like to consider another example of cylindrical geometry. So let's consider a cylinder. It's a solid cylinder of radius A, and this is an infinite cylinder. And the cylinder has a uniform charge density ρ, so ρ will be uniform. And the reason we make the cylinder infinite is we could use the same symmetry argument to say that the electric field is pointing away from this axis of symmetry. But unlike the wire, there's now going to be some field inside. And so we have two regions of space, 1 and region 2. And if I use a cylindrical coordinate system, then I can say that my region 1 is where the r is less than the radius or equal to the radius of the cylinder. These two regions will overlap where r is greater or equal to a. And because there's two regions of space, I'll need to apply Gauss's law twice for each region separately. I apply Gauss's law separately for each region. So again, we begin by, let's look at the region 1 for r less than or equal to a. So we draw our source, A, and now, just like for a wire, I'm going to pick a Gaussian surface of radius r and length L. And the flux will only be through the body of this surface, just like on the wire. And so our flux, charge enclosed over epsilon naught. The flux is the electric field inside this region times the area of the cylinder, because remember, flux is E field on the surface. So the area is circumference, 2 pi r times L. And the charge enclosed, well, the charge enclosed, because the density is ρ, this is just ρ times the volume of a cylinder. And the volume of a cylinder of radius r is ρ times the cross-sectional area A times the length of the cylinder. And we have to divide by our constant. And so you can see that we've calculated the electric field to be ρ over 2 epsilon naught. The L's cancel. And it goes like r. We'll make it a vector, r hat, for r less than or equal to a. And there is the electric field inside the Gaussian, inside our solid cylinder. Notice that this field grows like r inside. Now if we want to do the same calculation in region 2, we'll make our cylinder a little bit smaller, radius a. And now we choose our Gaussian surface. By the way, I should have shaded in the charge enclosed. We make our Gaussian surface. We use the same variable r, but now in this case, r is only bigger than a. We have a same length that doesn't matter, but remember, r is always greater than a. And you can see that the charge enclosed is all of this. There's no charge outside the cylinder. And so in this case, when we set the flux equal to the charge enclosed divided by epsilon naught, our flux will be exactly the same, E 2 pi RL. I could have said this is region 1, and this is region 2. The E field in region 2 points out, and the charge enclosed is only this. So instead of pi r squared, it has to be less. It's the cross-sectional area of the actual physical charge distribution, pi a squared times L over epsilon naught. And so this tells us that the electric field in region 2, when we solve for this, we get ρ over 2 epsilon naught times a squared. And now, just like the field of a wire, the electric field outside goes like 1 over r. And this is true for r bigger than a. Now, if you substituted a into both of these results, you can see you would have the same electric field on the surface. So that's good. And what we see is inside, the field grew like r, and outside, the field goes down like 1 over r. And as a simple exercise, you should try to make a graph of this radial component of the electric field.